Okay, we were solving this problem to determine U4. Let's see, what do we know? Oh, we know the volume. So V1 is the same as V4. So we know V1 is the same as V4. But we need another information. So let's see. This one. The specific entropy remains constant. So S3 should be the same as S4. And we know the pressure. No, we do not know the pressure. Okay, so since it is a isentropic process, we can use one of these two equations. And since we know V1, 3 and 4, let's say 3 and 4, we can use this relation. So V3 over V4 should be the same as VR3 over VR4. And since we know the temperature at number 3, we can find VR3 at 2150 Kelvin. What about VR4? We do not know VR4, so let's find it. So if you want to determine V3 over V4, we can say it's going to be V3 over V2 times V2 over V4. And according to this one, V1 is the same as V4. So we can say this one is V3 over V2 times V2 over V1. Then, if you look at here, we can determine V2 over V1 because we can use this relation. V2 over V1 is VR2 over VR1, and since we know the temperature at state number 1 and PR2 at state number 2, so we can determine VR1 and VR2. What about V3 over V2? What is the relation between V3 and V2? V3 and V2, it is a constant pressure process. So if you have a constant pressure process, you may remember this equation. Since this is an ideal gas, we are assuming air as an ideal gas, we can use this equation. Sorry. P3 over P3 times V3 over T3 is going to be T2 V2 over T2. We found this equation from chapter 3 when we studied ideal gas equation. So in this case, it's a constant pressure process between 2 and 3. T2 is the same as P3. So V2 over T2 is going to be V3 over T3. And we want to determine V3 over V2. If you divide each side by V2 and multiply by T3, then V2, V2, we can cancel them out. T3, T3, we can cancel them out. So V3 over V2 is the same as T3 over T2. So we can calculate V3 over V2 by T3 over T2, since T3 is given, and we can find T2 from this PR2. And for this term, we can find VR2 from this PR2 and VR1 from 300 Kelvin. So that's how we can determine the left-hand side of this equation. So let's do that. T3 is, by the way, 2150 Kelvin, and T2 we do not know. However, we can calculate that because we know PR2 is 105.04. So if the PR2 is 105.04, it is between these two values, 105.04. So if you want to determine the temperature and VR, you can do a linear interpolation between these two numbers for this one and these two numbers. So from here, you can find the temperature T2. If you do a linear interpolation, T2 is going to be 979.6 Kelvin. And VR2, do I have it? 26.793. 26.793. So we can use these two values. Here, VR2 is this one, 26.793, and T2 is 979.6. 979.6 Kelvin. So we have T2, T3, and VR2. So we just need to find VR1. Then, how can you find VR1? What is the temperature? The temperature is 300 Kelvin. So you can find VR1 at 300 Kelvin. So let's go find 300 Kelvin. Here we have 300 Kelvin, and VR is going to be 621.2. So I'm going to write this 621 here, 621.2. Then if you go back, now we have everything on the left-hand side. T3 over T2 is VR3 over VR2, and V2 over V1 can be found by VR2 over VR1. So we know everything on the left-hand side. We know VR3, so we can determine VR4. So if you do the calculation, VR4 is 22.98. So we just need to find U when VR4 is 22.98. So let's go back to this property table and let's find 22.98. VR is here, 22.98. It's not on this page. So let me go to the next page. 22.98. 20.98 is going to be between these two numbers. So we need to do another linear interpolation to determine U, which is between these two numbers. So if you do the linear interpolation, we get 785.75. So that is U4 in this problem, 78575. So here, this is 785.75 kilojoule per kilogram. So that's how we determine U1, H2, H3, and U4. So whenever you have a diesel cycle problem in the final exam, you need to show how you calculate U1, H2, H3, and H4, because after this, the rest of them is going to be pretty simple. Okay? So we found U1, H2, H3, and U4. So let's go calculate the compression ratio. How do we determine compression ratio? The compression ratio is the ratio between the bottom dead center and the top dead center. So V1 divided by V2. And we already know V1 divided by V2 from where? From here. V2 over V1. So the other way. So V1 divided by V2 is so the compression ratio, which is R, can be determined by the volume when the piston is at the bottom dead center, and the volume when the piston is at the top dead center. We can calculate this one by this equation, VR1 over VR2, and we already found these values, 621.2 divided by 26.793. So if you calculate the compression ratio, it's going to be 23.19. If you recall, the previous Otto cycle, the compression ratio in the previous problem was 8. Now you can see the compression ratio is almost 3 times of the Otto cycle. So this one has higher compression ratio. That means that higher fuel efficiency. The second problem is the cutoff ratio. The cutoff ratio is the volume ratio between 2 and 3. So cutoff ratio is R of C. This can be determined by V3 over V2. And we already determined V3 over V2. Here, V3 over V2 is T3 over T2. We already found them. And T3 is given, and we already found T2, which is 979. So we can determine VR of V3 over V2 simply by T3 over T2. This is 2150 divided by 979.6. So you get 2.19. That's the cutoff ratio. And the next problem is the thermal efficiency of the cycle. The thermal efficiency of the cycle can be determined by desired output over required input. This is exactly what we studied in chapter 5 when we studied heat engine, right? So what is the desired output? The net work, W net, and what is the required input? heat transfer in, Q in. So what is the net work? So this Diger cycle produces work during the expansion process and consumes work during this compression process. So it's going to be expansion process minus compression process. So this W net is going to be W34 minus W12 divided by where heat is added during the combustion process between 2 and 3. So it's going to be Q23. You can also simplify this equation by this way. Since we have to calculate 3 of them, you can also do this way. W net, according to chapter 5, W net is Q in minus Q out. So this can be rewritten as Q in minus Q out divided by Q in, which means 1 minus Q out over Q in, which could be simpler than this one. So in that case, where is heat transfer out between 4 to 1, and where is the heat transfer in between 2 and 3? So if you solve this equation, we get 1 minus H2 minus H3. I'm sorry, H3 minus H2. H3 minus H2. We already found the energy balance equation for each process last Tuesday. And, oh, that's a heat transfer in. My bad. So this one goes here. The thermal efficiency is 1 minus heat transfer out between 4 and 1, U4 minus U1 divided by heat transfer in between 2 and 3, H3 minus H2. And we already found all the values here, U4, U1, H3, H2. So let me just write it here. 785.75, 214.07, 2440.3, 1022.82. So we have everything. You can determine the thermal efficiency, which is 0.597, about approximately 60%, which is very high because we have a high compression ratio. The last one is the mean effective pressure. The mean effective pressure can be determined by W net divided by V1 minus V2. Finding W net is not a problem. That W net is going to be Q in minus Q out. We already, found Q in 2440 minus 1022, and Q out is going to be 785 minus 214. So the W net is going to be Q in, this one, 2440.3 minus 1022.82 minus this one, 785.75 minus 214.07. What about V1 minus V2? Oh, we only have the ratio. So in that case, this is going to be mass times, let's divide by volume. So how do we solve this one? We can divide by volume. So this is V1, 1 minus V2 over V1. Since we already know the compression ratio here, this is 23.19. 23.19. We just need to find V1. So how can we determine this V1? We can use TV is RT. So T1 V1 is R times T1. Do we know pressure and temperature at any moment? Yes. At the initial state, we have a 95 kilopascal and 300 Kelvin. So P1 is 95 kilopascal. R is the gas constant, 0.287 kilojoule per kilogram Kelvin, and the temperature is 300 Kelvin. So we have everything. You can determine the mean effective pressure. The mean effective pressure, if you do the calculation, we get 975 kilopascal. So whenever you have diesel cycle problem, the first step is going to be finding U1, H2, H3, and U4, and the other is going to be just use those values that you found to determine each of them. Okay? In the final exam, you will see one problem from this chapter 9. So you may see a problem related to Otto cycle that we studied last Tuesday, or this one. Any question? The last cycle that we are going to study is gas turbine. Gas turbine can be used in many places. One of them is going to be power plants. So gas turbines have several advantages over vapor power plants that we studied in chapter 8. The advantages are it's easy to construct because it's very simple, and it's much cheaper, and it can be smaller than typical vapor power plants. But there is one problem, which is one of the major problems, which is that the efficiency is low. However, these advantages can be used in some certain applications, especially when we do not want to use vapor as a working gas. So the problem of vapor power plant is vapor power plant, which is a Rankine cycle. So you may remember this Rankine cycle from chapter 8. We have steam generator and a turbine and condenser and pump. So what's going to happen is that, so there's a number 1, there's number 2, number 3, and number 4. So we produce this power here, W dot T, and we consume, the work, W dot P, and we have a heat transfer input here to the steam generator, Q dot in, and we have a heat rejection from the condenser by cooling fluid, Q dot out. So one of the advantages is that its back work ratio is very low. What is back work ratio? It's the ratio, how much power you need to consume from how much power you produces. So how much, the power we need to provide to run the pump, and back work ratio is almost, the 1 to 2%. So about 99% of the turbine power that you produce can be used to produce electricity. But one disadvantage of this Rankine cycle is the working fluid is water. Water is the working fluid. Then what is the limitation of using water? The water has the maximum temperature, which is called critical point. You may remember, when we have a PV diagram, there's a saturation curve, and right on top, this is called critical point. Above this point, water does not exist as water. It's going to exist as a supercritical water that has the characteristics of vapor and liquid together. So using supercritical water is very difficult, so we usually limit the temperature of the power plant below this point. So what about if you want to use vapor power plant in nuclear reactor? So usually the output of the nuclear reactor is very high. So to run a vapor power plant, you need to limit the temperature. And what's the problem of limiting the maximum temperature? If you remember chapter 5, heat engine, how do we determine the efficiency? The efficiency can be determined by 1 minus Q in over Q, The efficiency can be determined by 1 minus Q out over Q in. Then do you remember the Carnot efficiency, the maximum thermodynamic efficiency from a heat engine? How do you calculate that? The reversible heat engine has an efficiency 1 minus TL over TH. So what is TL? This is the temperature of the coolant. So if you want to improve this thermal efficiency, there are two ways. One is decreasing the coolant temperature, then it will increase the thermal efficiency, or increasing the temperature of the source of the energy. So can we decrease the temperature of the coolant? Not really, because we are using, the water from nearby river or lake or ocean, unless there's no unless, the temperatures are almost constant, so we cannot decrease the temperature of the cooling system. So that's not an option. So the only way to improve the thermal efficiency of a heat engine is to increase the temperature of the energy source. However, if you use water, the temperature TH is limited by this critical point. So that is the disadvantage. Then one can say, what about if we use, another fluid other than water? Yeah, we can do that. We can use, there are, the power plants that, the advanced power plants that use high pressure helium, sodium, or carbon dioxide. So we are trying to use different working fluid than water. But the problem is that if we use different fluid other than water, you cannot use Rankine cycle anymore. So what cycle do we have to use? Gas turbine. So when we have a gas turbine, the gas turbine does not rely on liquid vapor phase change, while Rankine cycle uses it. So we can use any gas for this cycle. So let's study, how we can do that. Okay. So this gas turbine consists of mainly three components. One is compressor. This compressor replaces this pump. So instead of pump, we are going to use compressor, and we are going to increase the temperature and pressure of the working gas. This working gas goes into a combustion chamber or heat exchanger, depending on how we deliver heat. Then it will increase the temperature and pressure even further, and then it enters the turbine, and it's going to expand in the turbine. That's how we produce net work. So the only difference between this gas turbine and the Rankine cycle is that we have a compressor rather than pump. Why do we need to use a compressor? Because we are using a working fluid that doesn't undergo phase change. When we have water, we use a phase change, so we don't need a compressor. We can just use pump. But this time, the working gas, they don't usually undergo phase change, so we have to use a compressor. That's the only difference. So by using compressor, now you can use many different types of fluids. However, there's one condition, one drawback of using compressor, which is compressor consumes a lot of work. So the backwork ratio of this compressor is typically very high, sometimes up to 40% to 60%. So that is the only drawback. Then how can we analyze this gas turbine power plants? We are going to use the same air standard analysis as we do in Otto cycle and diesel cycle. So let's do that. So our assumption is that in this air standard, it is called Brayton cycle. In this air standard Brayton cycle, our assumption is that this compressor and turbine are working as isentropic compression and isentropic expansion, and this heat exchanger where heat is added is going to be constant pressure heat exchanger. And to complete this cycle, in this air standard Brayton cycle, we are going to introduce a heat exchanger. That's where we reject waste heat. Okay, and that is also constant pressure. So we have isentropic compressor, isentropic turbine, and constant pressure heat addition, constant pressure heat rejection. So based on that assumption, these assumptions, let's solve this air standard Brayton cycle thermodynamically. So we are going to follow the same step as we did in Otto cycle and diesel cycle, which is we are going to make a PV diagram and TS diagram. Okay, so let's do that. So process 1 to 2 is going to be where the process 1 to 2. Isentropic compression. So let me draw PV diagram and TS diagram. And PV diagram starts from here, number 1. TS diagram starts from here, number 1. First of all, we have isentropic compression. This is a compression process, therefore volume decreases and pressure increases. So this process is from here to here. Number 2. What about on this TS diagram? The process 1 to 2 is isentropic compression. Isentropy means entropy S remains constant. And it's a compression process, therefore temperature goes up. So this way, number 2. And this isentropic compression is followed by heat addition at constant pressure. So constant pressure heat addition. So this pressure P should remain constant. And it is added, therefore volume goes up. So this is number 3. And it's a constant pressure heat addition. Heat is added, therefore temperature goes up, and heat is a waste form of energy. So when you gain more waste form of energy, entropy goes up, right? Because entropy is a measure. Entropy measures how much waste energy you have in the system. So if you get more waste energy, entropy goes up. If you reject waste energy, entropy goes down. In other words, when heat is added, entropy goes up. When heat is removed, entropy goes down, right? So this way, number 3. And then isentropic expansion. So this is an expansion process. Volume goes up, pressure goes down. So this way, number 4. And what about TS diagram? It's an isentropic expansion. It's an isentropic process. Entropy S remains constant. And it's an expansion process, therefore temperature goes down. Number 4. And finally, the cycle is completed by heat rejection at constant pressure. So constant pressure, heat rejection. Pressure remains constant. So heat is removed, so volume goes down. And what about here? It's a constant pressure, heat rejection. Heat is removed. In other words, waste energy waste is removed. So entropy goes down. And since heat is removed, temperature goes down this way. So here. So the enclosed area represents the net power this one can develop. Okay. So how can we improve the thermal efficiency of this Brayton cycle? Simply, we can compress the working gas even further. So we are increasing the pressure in the combustion chamber. So instead of this, we're going for even higher. So we are adding this much net power. So if we increase the pressure, which means that we compresses more then we can add this much power. So one of the main ways, one of the key ways to determine to increase the thermal efficiency of this gas turbine cycle, we are going to increase the pressure at the end of this compression process. So that's how we can improve the performance. And here is the information, how, the thermal efficiency can be improved, can be enhanced by increasing the compression ratio. So the efficiency goes up continuously as we increase the compression ratio. So if we compress more, we get higher thermal efficiency. But the problem is that if you want to compress more, you need to, consume more power in the compressor. So the downside of this thermal efficiency is greater back work ratio. So a relatively large portion of the work developed by this turbine is required to drive the compressor, because we want to improve the compression ratio to gain higher thermal efficiency. So for gas turbines, back work ratio ranges from 20% to 80%, which is extremely high. So if you produce, let's say, 1 megawatt of power from the turbine in a gas turbine, then about 20 to 80% of the power produced by turbine goes back to the compressor to run. So that power is going to be much less. If it is 1 megawatt power plant, the actual, the turbine power it produces is going to be maybe 3 megawatts or 2 megawatt, way greater than the net power it develops. So that's the downside. But the good thing is that we can achieve higher efficiency, and also this gas turbine is cheaper and much simpler than Rankine cycle. So, but as you can see, the back work ratio for vapor power plant is only 1 to 2%. Why? Because in a vapor power plant, we don't use compressor. We use pump. Pump is way cheaper than compressor. Okay? Then, let's solve this air standard Brayton cycle by thermodynamic equation, which is energy balance equation. So how can we do that? We have compressor, and it's going to be run by turbine. So while turbine is running, it's going to, to provide power to run the compressor because they are coupled. And once working gas is compressed, it enters combustion chamber or heat exchanger in this air standard Brayton cycle, where heat is added, Q in. It's a constant, it's a open system, so we are going to add a dot on top of it. Steady state open system. And after heat is added, it's going to enter the turbine to produce power. So there is a net power is developed, W dot net. And this net power is going to be W dot T minus W dot C. So the turbine power minus the compressor power, because the compressor is driven by this turbine. And then this cycle is going to be completed by a heat exchanger, where we reject any waste heat, do that out. So the inlet of the compressor is number 1, the inlet of the heat exchanger number 2, the inlet of the turbine number 3, the inlet of this heat exchanger is number 4. So how many energy balance equation do we need? One for the compressor, and one for this heat exchanger where heat is added, and one for this turbine, and one for this heat exchanger where heat is rejected. So 4 energy balance equations. And it's not that hard because now you know it's an open system. So we are using specific enthalpy H. So we just need to determine the direction of H2, H1, H3, and H4. We did this many times. From vapor power plant, Otto cycle, diesel cycle, this is the last one, Brayton cycle. So let's determine the energy balance equation for this compressor. So this compressor consumes compressor power, W dot C. So how many energy transfers into the compressor? 1, compression power, and H1. H1 times the mass flow rate, times mass flow rate, times mass flow rate. That is because H is a specific enthalpy. The actual rate of enthalpy is going to be m dot times H, m dot times H. So here, the energy balance equation can be determined by this way. W dot in should be the same as W dot out, which is what we studied in chapter 4. So what is W dot in for this compressor? W dot C and M dot H1. W dot C plus M dot H1. These two are the energy transfer into the compressor. And how many energy transfer out of this compressor? Just one, M dot H2. M dot H2. So that is the energy balance equation for the compressor. By the way, we are neglecting kinetic energy change and potential energy change. What about this heat exchanger? How many energy transfer in? 1, M dot H2, and 2, Q dot in. There's only one energy transfer out, M dot H3. So now we know how to make this energy balance equation. M dot H2 plus Q dot in is going to be M dot H3. What about this turbine? How many energy transfer in? Just one, M dot H3. How many energy transfers out of this turbine? M dot H4 and the turbine power. M dot H3 is going to be M dot H4 plus turbine power. The last one is this heat exchanger where we reject any waste heat. How many energy transfer in? M dot H4. M dot. And how many energy transfer out of this heat exchanger? M dot H in and Q dot out. So these 4 are the energy balance equation. And how can we determine the thermal efficiency? The thermal efficiency can be determined by desired output W dot net over required input Q dot in. So where is W dot net? W dot net is W dot T minus W dot C. So W dot T is here. If you move this one to the left hand side, M dot H3 minus H4 minus W dot C, which is here. If you move this one to the right hand side, M dot H2 minus H1 over Q dot in is here. If you move this one to the right hand side, M dot H3 minus H2. You can cancel M dot out. So that's how you determine the thermal efficiency. Is that what we did here? Yeah. The last one is the backwork ratio. The backwork ratio is how much compressor consumes, how much power compressor consumes from the power turbine produces. So the backwork ratio can be determined by compressor power divided by turbine power. So what is compressor power? Where is compressor? Oh, here. So if you move this one to the right-hand side, it's going to be m dot h2 minus h1. M dot h2 minus h1. What about turbine power? It's right here. If you move this one to the left-hand side, m dot h3 minus h4. M dot h3 minus h4. So this one slide has every thermodynamic analysis that you need to know about this Brayton cycle. So that's it. Based on that, let's solve one problem together. It's going to take maybe 3 or 4 minutes because it's very simple because of this word cold air standard analysis. You may remember when you see cold, that means that specific heats are constant. So we can use them instead of using a table. Okay, so let's solve this problem. We want to determine the thermal efficiency of the cycle, which is here. So we need to know H1, H2, H3, H4, and the backwork ratio, which is H1, H2, H3, H4. Either we can cancel them out. And the net power developed can be determined by m dot H3 minus H4 minus m dot H2 minus H1. Sounds like if you know H1, 2, 3, 4, and that's all. However, it says cold air standard Brayton cycle. Whenever you hear this cold, that means that you must be very happy because you can use a specific heat. If you use a specific heat, and what is the equation? H2 minus H1 is simply Cp T2 minus T1. So you don't have to find H1, H2. You can just calculate H2 minus H1 by using specific heat. So let's do that. The thermal efficiency of the cycle, which is here. The thermal efficiency of the cycle is, H3 minus H4 minus H2 minus H1 over H3 minus H2. Oh wait, it is a cold air standard Brayton cycle. That means H3 minus H4 is Cp T3 minus T4. So this thermal efficiency equation can be written as Cp T3 minus T4 minus Cp T2 minus T1 over Cp T3 minus T2. Then do we need to calculate Cp? No, you can cancel them out. So as long as you know the temperatures at each state, you can determine the thermal efficiency. What about backwork ratio? Backwork ratio is given here. Backwork ratio is H2 minus H1 over H3 minus H4, which can be determined by Cp T2 minus T1 over Cp T3 minus T4. So you don't have to determine H1, H2, H3, H4. You can calculate backward ratio by just the temperatures at each state. What about the net power? The same thing, same continues. The net power W dot net is going to be W dot T minus W dot C. So where is W dot T? Here. M dot H3 minus H4 minus M dot TH2 minus H1. Are we going to determine H? No, we can use a specific heat. M dot specific heat T3 minus T4 minus T2 minus T1. Okay? So, what we need to find? H1, H2, H3, H4? Not anymore. We just need to find T1, T2, T3, and T4. So, let's see. T1 is given 300. Very good. And the turbine inlet, where is turbine inlet? Turbine inlet is number 3. So T3 is 1400. So we just need to find T2 and T3. Then that's it. So how can we do that? The compressor pressure ratio is 10. What is the compressor pressure ratio? How much compression you can make. So it's going to be P2 over P1 is 10. Then can we use this ratio somewhere to determine temperature T? Yes. In chapter 6, for an isentropic process, I'm sorry, I said chapter 6. Today is the last class, so it's time to have a break, right? So you may remember this equation. T2 over T1 is P2 over P1 to the power kappa minus 1 over kappa. You remember that from chapter 6. Now you can use that equation because it's a cold air standard analysis. Whenever you have a cold air standard analysis, you can use this equation because the assumption for this equation is constant specific heat. Why didn't we use this simple equation in the previous Otto cycle and diesel cycle? Because they were not cold air standard analysis. They were just air standard analysis. So it is very important when you solve a problem in chapter 9, that you need to check whether it is just air standard analysis or cold air standard analysis. Which one is more accurate? Of course, just air standard analysis, because this one you assume that constant specific heat anywhere, even at 300 Kelvin, 1400 Kelvin, which is not realistic, right? So let's do that. P2 over P1 is T2 over T1 to the power kappa over kappa minus 1, right? The other way, right? Then 10 kappa is what? 1.4. 1.4. T1 is 300. Can you determine T2? Yes. T2 is what? 579.4 2 7. What about here? We can use the same thing. P3 over P4 is 10. That is T3 over T4 to the power kappa over kappa minus 1. So what is P4 over P3? That is 10. So T3 is 1400 Kelvin. Kappa is 1.4. Kappa is 1.4. We have everything. Can you determine T4? Yes. That is 725.13 Kelvin. Now you know all the temperature values. And specific heat. Do we know specific heat? Let me give you the specific heat. It's 1.005 kilojoule per kilogram Kelvin. Now m dot is what? 6 kilogram per second. T1, T2, T3, T4, they're all given. T3, T4, T2, T1, T3, T2, and all of them, they're all given. So we can solve all of them. So what is the backwork ratio? 0.4137. What is the thermal efficiency? 0.482. Excuse me. What is the net power? 2385.9 kilowatts. So look at that. The thermal efficiency is high because we can increase the temperature at the turbine inlet, 1400, which is much higher than the critical temperature of water. So if you use Brayton cycle, you don't have to decrease the temperature down to the, you don't have to decrease the temperature to use water. Not anymore. So that's good. So we can achieve high efficiency. Then what is the downside? Since we are using compressor, the backwork ratio is 41%. So that is not very good, right? So there's a downside, there's a good side. So, the comparing vapor power plant and this gas turbine is more likely, when the temperature of the source of the heat is below the critical point of water, it is recommended to use Rankine cycle because it has very low backwork ratio. So the efficiency is high. On the other hand, if the temperature of the heat source, which is like, is very high, it's like a nuclear reactor, it is more recommended to use Brayton cycle. So presently, most commercial nuclear reactors are using water, Rankine cycle. But most advanced nuclear reactors that people are researching right now, they are using Brayton cycle. Because what is the problem of nuclear reactor? Increasing temperature? No. Limiting the temperature is the problem. Because the increasing temperature is pretty simple. And we don't want that to happen. We want to limit the temperature, so that we can use water. That is light water nuclear reactor. And if you want to increase the turbine inlet temperature slightly, then people use heavy water nuclear reactor because that has slightly higher the maximum allowable temperature. But if you use a gas turbine, you can increase that significantly because you don't have to rely on water. Okay? So that's everything about chapter 9. So we have about 5 minutes. So let's discuss, how you're going to prepare the final exam. You will see 3 or 4 problems. And There are 3 chapters, chapter 6, chapter 8, and chapter 9. So we studied vapor power plant in chapter 8. You will see one problem for sure. And chapter 9, we studied Otto cycle, diesel cycle, and Brayton gas turbine. You won't see Brayton gas turbine in the final exam because there are too many, the cycles that you need to study. And I know that you have to study many, many courses, right? So to save your time, there's no Brayton cycle. And one more thing, there is no fold analysis. So it's going to be either the Otto cycle problem in the PowerPoint or the DJ cycle problem in the PowerPoint. We solved the DJ cycle problem today and the Otto cycle problem last Tuesday. So, and you may remember how to use table 822 using VR and PR. So practice them, okay? And I don't have to explain anything because we have the easiest problem. We solved 2 problems in the PowerPoint, the easiest one and the most difficult one. The problem that you will see in the final exam is going to be between that 2. What about in chapter 6? So there's one problem here, one problem here. So this chapter 6 is going to be maybe 1 or 2 problems. And there are 2 areas. One is isentropic efficiency. The other one is entropy balance equation to determine entropy generation. Okay, so you will see both of them or just one of them. Okay. Any question? 1 hour, 3 or 4 problem here at 10 o'clock next Tuesday. Any question? Okay, good. Then that's all about it. And I hope you enjoy winter break. And yes.